Okay, class, greetings from my deathbed. Or not my deathbed, as you can see, rather my garage. I'm actually feeling a little bit better, but the rest of my family is quite sick, and to not have the background noise of somebody puking, we're doing this from my garage, so, enjoy my license plate collection. Alright, let's talk about the midterm exam. As the time of recording this, 10:30 a.m. on Tuesday, I've gotten a few questions from people on things I'd like covered. The vast majority simply state, will you make sure to go over such and such a bullet point on the list? So somebody said, just go over all of them. So we're going to do that. There were a couple other things. Somebody asked if I would post any additional YouTube videos that might help. So that's a really good suggestion. I'll make a point at the end of this video to pull up all the YouTube videos related to this content. If you want to watch things worked out, that'll be one way you can do so. And then the other one is somebody wanted to know all the detailed list of properties associated with each crystal structure, like how many atoms are there, the coordination number, stuff like that. So we'll do that. So let's just go ahead and start from the top. Let's start with steady state creep strain rate, solving for the different coefficients for that, right? For K and Q from a plot of strain rate versus 1 over T and strain versus time. So let's dive into that. So remember, with creep, when you initially load it, there's going to be some strain, but creep is specifically talking about the strain that occurs slowly over time. So if you have the following plot, let's say you've got strain, total strain over time, t, over there. When you initially load it at time t equals 0, there will be some instantaneous strain, right? It will strain a little bit. But then over time, you have 3 regions, right? You've got 3 regions. You've got primary creep, secondary creep, and tertiary creep, right? And only secondary creep, that region in the middle, has a constant rate, right? Rate meaning the rate, the strain slope as a function of time, that's flat, right? Because that's flat, that allows us to then predict it. We can predict off of this. So if we go back to our plot, let's see, this was in chapter 9 that we talked about this, failure. We saw instances of this. Yeah, so here we are. There's our strain versus time. And we saw that different temperatures and different stress can change the slope, right? They can change that rate. For example, higher temperatures, right? This would be up here. That's going to increase the slope. Lower temperatures can bring down here, higher stress, lower stress. So what we really need is an expression that accounts for temperature and stress, and that's what this strain rate expression is. So let's go back to our review. The strain rate expression, epsilon dot, is equal to a constant K, the applied stress, sigma, raised to the n, multiplied by the exponential of negative Q, that's an activation energy for creep, over RT. Right? So that is the plot of strain versus time. What about the other plot? Well, the other plot, let's draw it right here. In this one, we're going to plot on the y-axis natural log of strain rate. We could plot actual strain rate and show it on a logarithmic axis and get the same effect. But on the x-axis, we're going to plot 1 over temperature, 1 over T. And in this plot, if we were to plot our data for strain rate, we would get a straight line, right? And the slope of this line is going to be equal to negative Q, our activation energy for creep, over R. How do we know that that's the case? Well, if we start with this expression, it is not linear. And the only way to make it look linear is to put it on a log axis, or by taking, log or natural log of the strain rate. So let's go ahead and do so. If we take natural log of this, natural log of the strain rate, that's going to equal natural log of K plus n times the natural log of sigma plus negative Q over R multiplied by 1 over T, right? So all of a sudden this looks linear. There's our Y, that's X. No, sorry, M, that's our slope. No, that is X, I'm sorry. X this becomes m, and this becomes b. Okay, y equals mx plus b. So it's important to know that if I gave you a plot like this, where it's either natural log of the strain rate, or if I plotted the actual strain rate on a log axis, you could use that plot to determine the activation energy from the slope. You could get Q by taking the slope. In other words, if you had a point here and a point there, let's call this x2, y2, we'll call this x1, y1. You could do rise over run, right? In this plot, it's shown as natural log, so you could do directly, you could do that negative Q over R, in this case, equals y2 minus y1 over x2 minus x1, and you could solve for Q. The only thing to do differently, if this was shown not natural log of strain rate, but rather actual strain rate on a log plot, is instead of taking y2 minus y1, you'd have to take natural log of y2 minus natural log of y1, and then natural log of x2 minus natural log of x1. Otherwise, it's the exact same approach, okay? So that's how you would solve for Q from this plot. How do you solve for K and N? The way that you solve for K and N is you need to be able to write, since you have two unknowns, you're going to have to be able to write two equations. So on the test, you're going to be given information in this secondary region, right? You're going to be given information there, and you're going to be given it at either two different temperatures or two different stresses. Let's say that they're at the same temperature but two different stresses. If the second stress is larger than the first stress I've drawn here, it's going to have a higher slope, right? This might correspond to sigma 1. That's sigma 2. We would say that sigma 1 is greater than sigma 2. So how do you solve for K and N? Well, you can take the slope of these two expressions. So you've got strain rate 1, sigma, or epsilon dot 1, and this would be epsilon dot 2, okay? So you know that what the strain rate is for these different values. So we could say that strain rate 1, epsilon dot 1, that's equal to K, which is a constant, multiplied by the stress 1 raised to N, exponential of negative Q over RT. Meanwhile, epsilon 2 dot, that's equal to K sigma 2, a different stress, to the raised to the N, multiplied by exponential of negative Q over RT. In both these cases, the temperature is the same, we would have said. In that case, if you were to divide these two expressions by another, these whole terms would cancel out. K would cancel out. You know those two strain rates by solving for the slope. You do the slope the exact same way as before. You pick 2 points on here, and it's y2 minus y1 over x2 minus x1. So you've got the slope for those two different things. Therefore, you've got epsilon 1 dot and epsilon 2 dot. You know what the stresses are, so you can solve for N. The way that you do that, let's go ahead and just write it out. Okay, so epsilon 1 dot over epsilon 2 dot equals sigma 1 over sigma 2, this whole thing raised to the N. To solve for N, if you can't remember how to do this, you take natural log of both sides, and it allows us to do it the following. Natural log of epsilon 1 dot over epsilon 2 dot is going to equal N multiplied by the natural log of sigma 1 over sigma 2. So N will simply be equal to natural log of epsilon 1 dot over epsilon 2 dot divided by the natural log of sigma 1 over sigma 2. Okay? So you can solve for N very easily. Once you know N, go back to these expressions, and you can solve for K with the same approach. You would have already solved for Q, right? You solved for Q here, so you know what Q is. Let's assume that you're told what the temperature is. So you know everything in here, you can solve for this. You know a stress, you know this exponent N, and you know the strain rate, so you can solve for K. So it's pretty straightforward. how you solve for these. Okay, what else can I say about that? I think that's everything on those ones. If it's unclear, when I post this on YouTube, go ahead and leave a comment, and I can either, if it's easy to answer, I'll follow up in a comment. If it requires another video, I can post another video. That's no problem. Meanwhile, let's pull up an example of where you can see this as a YouTube video. I'll pause the video for 1 second. Okay, so I've posted here a link to a solution where we worked through a similar problem on that. So you'll be able to see this pop up. If you want to see one worked out in all its gory detail, where we figure out Q, we figure out N, we figure out K, you can see it here on YouTube. This sort of pops up. I'm in my garage where I have crappy internet, so I'm not going to do that. Okay, next thing on the list is Griffith fracture toughness. Okay, Griffith fracture toughness. Let me grab that. All right, for Griffith fracture toughness, we use Griffith fracture toughness for brittle materials that are going to fracture when a flaw size gets too large. So we have K, and K, that, remember, is our stress intensity factor. It's equal to the stress at its maximum divided by the stress that you applied. So you apply a stress, you applied 100 megapascals, but because there's a flaw in your material, in the vicinity of that flaw, it gets magnified and you see a larger stress. So maybe in the vicinity of that flaw, maybe it's 1,000 megapascals. So then your stress intensity factor would be 1,000 divided by 100 would be a factor of 10, right? So there's a critical stress intensity factor. We call that K1, as in like the Roman numeral 1, C for critical, K1C. This is the stress intensity factor at which you will get failure, and it is equal to the following. Y, that is the unitless shape parameter. It takes into account the geometry of your flaw and the shape of it, multiplied by the stress, multiplied by pi times your critical flaw size. Okay? This is Griffith's fracture toughness equation. For any applied stress and flaw size, you can calculate the right-hand side of this equation, right? Let's say, just to throw some numbers out, let's say that your flaw size is small. If A over W is small, then we know that Y equals 1.12. If A over W is large, I would have to give you a figure, and you would have to calculate A over W from that. Okay, that's not going to be on this midterm. It was on the homework. Okay. If the flaw size is small, for a given stress and a given flaw size, you could calculate whether it would cause failure in your material. Let's just throw some numbers out. I'm just guessing here, so I don't know how it's going to turn out. But let's put 1.12, let's assume 100 megapascals. And let's assume that we have a 1 centimeter long flaw in your material. So I'm going to go ahead and put this into meters. So 1 centimeter, 0.01 meters. Okay. We can go ahead and plug all that in. I'm going to pull it up on, let's do this. Let's pull up the virtual TI because I left mine at work. And let's say, meanwhile, while that's pulling up, let's say that our material, K1C, for our material is equal to, I don't know, 20 megapascal root meters. So, under these conditions, would you expect your sample to fail? Will it break or no? Okay. To figure that out, we're going to pull up our calculator. Okay. We're going to punch it in. We're going to just punch in the right-hand side of the equation, and we're going to see if it's larger than the left-hand side of the equation. The left-hand side of the equation is currently 20 megapascal root meters. And the right-hand side we're going to solve for real quick. So it's going to be 1.12 multiplied by 100. We could put in the units of pascals we want. So we could say e to the 6th. We can actually type this in. We don't need to, but why the heck not? I'll show you how to do this. So that's 1 megapascal, that's what the e to the 6 is, 1 million pascals, multiplied by, we're now going to do a square root, we're going to do pi, is right there, multiplied by our length, which is 0.01. We have to now put in units of distance, which is meters. Close this and we hit enter. Okay, and we get something with the units that we're not interested in, but that's okay. We can convert this. So I'm going to convert this. That's what the little triangle button is, the yellow triangle up there. That means convert it to different units. We're going to take that underscore large P alpha for A multiplied by underscore meters. This is faster on a calculator, right? Okay, so the answer is 1.985 e to the 7 Pascal root meters. So if we divide that by 1 e to the 6th, I'm going to go up and grab this value. I'm going to delete off the units now. And I'm just going to divide this by 1. Garage light has to flip on. 1 e to the 6th. This tells us, how about that? Our fracture, the right-hand side of our equation is 19.85 megapascal root meters. Okay? So over here, this equals 19.85 megapascal root meters, which is just less than our actual fracture toughness. Therefore, this technically, using Griffith fracture equation, you would predict it to not fail. Kind of amazing that it was that close when we just spitball numbers. Okay, that's Griffith fracture toughness equation. So we could work this other way. I could say, given this fracture toughness, what's the largest flaw, or what's the maximum stress given this fracture toughness and this flaw size, right? Given two variables, you can solve for the third in this equation. Okay, that is Griffith's fracture toughness. Let's go to the next one. Okay, crack growth equation. Okay, the crack growth equation. If we go back to chapter 9, where is it? Chapter 9. Something that we learned about before we got to creep was that a flaw can grow over time, right? So for example, here's our crack length on the y-axis, and on your x-axis you've got your number of cycles. And we know that as you cycle something below the limit that Griffith fracture would suggest that it fails. So for example, I'm going to close this. To review. Okay, right here, for a given fracture toughness and for a given stress, we know that there's a critical flaw size. We're assuming that we're smaller than that critical flaw size. Maybe it's this big and we're only this big. But over time, this thing can grow, and as soon as it gets that big, then it fails. So the question is, how many cycles at this lower stress will it take before it grows to that point? That's what this equation allows us to calculate, okay? And the flaw size is going to grow at different rates. First off, it's not linear growth. It's this exponential growth, right? It's a power law growth. And higher stresses cause it to grow faster. Therefore, we need an expression that looks like this. dAdn, that's our incremental crack growth, right? That's the growth in the crack with each cycle. Each crack, it's the instantaneous growth. It's equal to A multiplied by the range in our stress intensity raised to the n. So what is the range in our stress intensity? Delta K. Well, K normal is just right here. That's our Griffith fracture toughness. The range looks the exact same, except instead of having a single stress value, it's the maximum minus the minimum. Okay? It's the range in stresses that it experiences. The only catch is that, remember, for this class, we are making the assumption that cracks only grow during tension, meaning positive stresses. So if I told you that a sample was subjected to an oscillating load between negative 200 megapascals and positive 200 megapascals, you would ignore the negative component and you'd only account for the positive one. You'd say that the stress range is 200 minus 0. Okay, that is delta K. So now that we remember what that is, let's go ahead and pull it up. You've got dAdn equals A, capital A, this is just a constant, delta K, that's the range in our stress intensity, raised to the n, a crack growth constant. So we remember that delta K is going to be equal to Y, our dimensionless shape parameter for the crack, delta sigma, which is just sigma max minus sigma min, only for positive values, multiplied by, here we go, our flaw size multiplied by pi in the square root. Okay, so we can, this alone is not very helpful, but we can separate the variables, which are dA and dN, and then we can integrate over both of those. We can solve for the number of cycles till failure, right? So if we've got dN by itself over here, and we've got dA over A delta K raised to the n over here, we can integrate from our initial flaw size, A0, up to our critical flaw size. We can integrate from 0 cycles up to the cycles at which it fails, n sub f. And what we will find is that we end up with the following expression. NF is equal to 1 over A, our crack growth constant. It's going to be delta sigma to the n. It's going to be pi to the n over 2. It's going to be the integral of our initial flaw size to our final flaw size, dA, over A to the n over 2. And this is going to be y to the n. Okay? So if, as it grows from its smallest size to its largest size, over that entire range, if the flaw size is small, meaning A over W, the crack size over the width of your sample, is small, that means that y technically is constant and it doesn't depend on the crack size, and you can take it out of the integral. Technically, we know that y is a function of the flaw size. If we go back to chapter 9, we can see that. We see that y is right, where is it? Right here, right? Here's y plotted as a function of A over W. Here's A, your crack size, W is your full width. So technically, as it gets larger, say when it's halfway across, y is a very different value. It's only in this limit of it being small that it's a constant. So if we assume that it's a constant, then we could bring y out of the integral. Okay, so solving for this is straightforward. You're going to take the integral. So if you need reminders on how to do these integrals, I'll refer you to my video where I've actually solved it in all its gory detail. You're going to plug in A and N if those are given. You remember on your homework, which was due last week, let's see, homework 4, that you can solve for A and N if I give you plots like this, right? If I gave you a plot of D8 over DN and delta K, and I show this on a logarithmic axis, you can take the slope of this to get A and N, right? So the slope is going to be, again, rise over run. And since I haven't plotted natural log of dA over dN, but rather shown on a log scale, then you have to not just take y2 minus 1, you have to take natural log of y2 minus natural log of y1. Same thing with x, natural log of x minus natural log of x1. That will give you the slope, right, n. Once you have the slope, you can take one of the values off of this plot. I took 0.1 because it's easy to see that it's at 100 for your x value. So you know what the x value is, or not. It's actually not at 100, it's at 60. Sorry, I misread that. Oh, 0.01, sorry, right here, 0.01. So it's at a stress range value of 60. There's your dA over dN. You know what n is, so you can solve for A, okay? So that's the A and the n. Now, if I go back to what I've said here, I just say crack growth equation. I don't state specifically on here that you need to solve for A over N, so that's not going to be on the midterm. So you will just be asked to use this equation, okay? Now, what about A naught and A0? A naught will probably be given in the question. What about A critical, excuse me? A critical you can solve by enacting Griffith fracture equation. You can say, okay, as this thing has a cycling stress, at the maximum stress at which it's cycled, what is the flaw size that would cause it to break? Here you're not using delta sigma, right? Delta sigma is only for delta K, but when it breaks, it's going to be at the maximum stress, not the range of the stress, the maximum stress. So you would take its K1C value, take its sigma value, and you could solve for the critical flaw size. Once you know the critical flaw size, you would know the bounded integral. You know how to take the end of the integral in the beginning, okay? That is crack growth. Okay, let's keep going. Actually, real quick, let me pull up an example video. I think I can just take it from from our notes. I'll pull up the one that we used here. So 2 things. First off, here's one using Griffith fracture toughness. So just put that right there. Okay, that's how you use Griffith fracture toughness, and then how to use the crack growth equation. We've got a video for it right here. If I can find it right here. Okay, so take a look at those if you need a reminder, especially this one because it'll go through the details of the integration. If you have questions, shoot me a comment or an email. I'll get to it. Okay, let's move to our next one. Okay, anisotropy. Anisotropy was defined as if you measure a property, whether that's a physical property, electrical, thermal, whatever it is, if you measure it in one direction, you get one result, and you measure it in a different direction relative to the crystal, then you have an anisotropic crystal, right? So let's say that we're measuring thermal conductivity of a clay. Let's pull up actually we can take it from our notes. Because I have no internet out here. Let's go to our crystal structures. And let's pull up clay. I think we saw clay as the silicates. Okay, right here. Okay, I'm gonna grab this. This is a type of clay, it's kaolinite. Let's say that we were trying to determine whether or not this was an anisotropic crystal, right? And to do so, let's say we measured electrical conductivity or thermal conductivity, right? And in one case, you were able to measure thermal conductivity in this plane. And then in the other case, you're able to measure it in this plane. And you get very different values, right? So if this is K kappa, we call it, that's for thermal conductivity, the ability for it to conduct heat. And this would be kappa 2. You would find that kappa 1 is much greater than kappa 2. It conducts heat much better in those planes than perpendicular to those planes. And the reason why is because this is all covalent and ionic bonding in these planes, and this is hydrogen bonding, and so that's the van der Waals force. It's a weaker bond. It's much less capable of conveying heat across this gap in the plane. So this would be an example of an anisotropic crystal, right? Whereas other materials, like if we go back to chapter 3, and we take something, particularly the cubic compounds are very isotropic. If we go to say FCC cubic, right? This one, because we can rotate this thing in so many different ways, we get the exact same thing. They tend to be much more likely to be isotropic. Now, there still might be directions where you get higher and lower values because technically bonding does change in different directions. But the principle of anisotropy versus isotropic is that if you measure it in different directions, and you get different values, it's anisotropic. If you get the same value, regardless of which direction you measured in, it's isotropic. Okay, let's talk about our next one. Okay, single crystals versus polycrystalline materials. Okay, single crystals versus polycrystalline materials. If we go back to our discussion of this, what we were talking about, let's take a sample as it's being cooled down. So you've got liquid, and as it's cooled down, it can become one of 2 things, right? You can have a bunch of small spots which start from the edges and then grow, right, until it's all sort of solid. We call this polycrystalline. Or if you grow it really carefully, you can actually cause this thing to grow into a single crystal, where all the atoms, all the way through this thing, are oriented in one crystallographic orientation. Meaning, if I were to draw like the 110 direction in this, that would exist all the way through the crystal. Because at no point is there like a grain, like imagine this guy, he's growing this way. But the one next door might be very, very different. Right? It could be growing different. And that leads to these grain boundaries, these regions where there's a messed up lattice between them. So polycrystalline versus single crystal materials, that's the difference. Now you might ask yourself, which one is going to be more likely to be anisotropic, right? If you have a polycrystalline ingot, these things are all randomly oriented one to another. So on average, there's essentially all the different crystallographic orientations. So it wouldn't matter if you were measuring thermal conductivity in different directions because they're all just random. Whereas here, depending on your crystal, if it's an anisotropic crystal and you have a great big single crystal of it, then there you might be able to see anisotropic properties. Okay. All right, let's go to our next one. Okay, this is sketching or label points, directions, and planes using Miller indices. Okay. Okay. Sketching or labeling points, directions, or planes using Miller indices. So let's sketch a few first. Let's sketch the following. Let's sketch the 0, half, 3/4 point. You know that's points because I use round brackets and commas. Let's sketch the 2, 1, half. Let's do -1/2, right? Direction, right? Those shouldn't have commas. 2, 1, and -1/2. And that technically would always be shown as 4, 2, or 1. Okay? We're going to show that direction. And let's show this plane, the, I don't know, the -3 or 3 bar, 1, 2 bar plane. Okay, let's go ahead and do those. So to do those, let's start by drawing a nice unit cell. Okay, we've got our unit cell. Let's pick an origin. I always think it makes sense to put it in the back left corner where possible. Okay, let's put it there. So in that case, the direction's the first thing we need to do. So, or the point, sorry. The point is 0 in the x direction, half in the y. So we're going to go over by half in the y, not the x. And then we're going to go up 3/4. So it would be that point, right? That would be the point 0, 1/2, 3/4. Because it's a point, we need the commas and we need the round brackets, okay? Now we can draw the 4, 2, 1 direction. Okay, to do this one, okay, to draw directions, I actually think it's easier to make it so that the longest direction is still within the unit cell. So I'm actually going to divide these all, instead of making them integers, I'm going to divide them until the biggest one is still only 1. So I'm going to divide this all by 2. So our direction becomes 1, 1/2, -1/4. Okay? I'm going to pick this top back corner for our origin, and we're going to go forward 1 in the x direction. We're going to go forward 1 in the y direction. We're going to go down 1/4 in the z, and that would be our direction. Okay? I think it's easier to do that than trying to draw multiple unit cells out. Try and make it fit within one unit cell is easier. Okay, that's that direction. Okay, now let me switch colors and we'll draw the plane. The plane is the 3 bar, 1, 2 bar plane, right? So let's pick an origin. Let's pick this back corner to be our origin, okay? Actually, we're going to go back in the x and the y directions. So let's pick this to be our origin right there, right? So the rule with these, remember, is you take our 5 steps that we established previously, and we're going to work them in reverse, right? So the final step, after was to turn it into integers. Before that, we needed to invert it. So let's go ahead and invert this. So that's going to be -1/3, 1, and -1/2. Those represent the axes where it intersects, right? So if this is the x, y, and z, then it intersects the x at -1/3 of the way back, right there. Intersects the y at -1/2, right there. And it intersects the, oh sorry, I drew that wrong, sorry. Intersects the y at +1, I drew this wrong. All right, we're gonna have to use another unit cell, my bad. That's okay, we'll draw another unit cell over. It'll give us the same cell, or the same plane. It's just less convenient. Okay. So it intersects the y-axis at 1, x at -1/3, and y at -1/2. Oh, geez, I picked a terrible origin. It's all right, it still works. So that's this next unit cell down. Okay, so you've got 3 unit cells there. If I draw this, intersects the y at -1/2. or the z at -1/2, excuse me. So it's this plane. So that's our plane. Not a great choice of a unit cell. It would have been wiser to pick this guy up here as a unit cell. If we draw the same thing there, let's do the exact same exercise. We go back 1/3, we go forward 1, we go down 1/2. So it does not matter which origin you use when you draw these things. It gives you the exact same plane because these planes run infinitely through the material, and so it doesn't matter which one you choose, you're going to get the same plane. It's just going to cut through a different unit cell. Okay? That is drawing these things. What about labeling them, right? So the other way is, instead of me asking you to draw them, I could ask you to label them if I already drew them. So let's do a couple examples of that. So let's draw a unit cell. Okay. What about the following? Okay, let's say you've got a point that's right here and a point that's right there. I want to know that direction. Okay, so whenever it's a direction, the foolproof way is to take final minus initial. Take the points of the final minus the initial. So you need to establish an origin. Let's try this one. That means that this guy out here, that's located at, in terms of x, y, and z, that's 0, 1, 1 as a point. This one over here is at is at 1, 0, and half. So you could take final minus initial. You could take the final x minus the final, or the initial x, final y minus the initial y, and so forth. But I think an easier way to do this is to just ask yourself, okay, as it starts here and goes there, what does it do with x? It goes back 1 full unit cell. Therefore, my direction needs to be 1 bar in the x. It goes back 1x. Now, it goes forward 1 in the y direction. This could be positive 1. And in the z, it goes forward by 1/2. Right? And then we turn this into integers instead of fractions. Right? So this becomes 2 bar to 1 direction. Okay? That would be labeling that. Let's label a plane. Okay? Let's pick something funky. This thing intersects it at, actually, let's do one. How about this? Okay. You've seen planes like this in the homework, but how would you label that plane, right? First off, the origin that we had before doesn't work anymore because the plane passes through it. That was our first rule. If the plane passes through the origin, pick a new origin. So, okay, we can do that. Let's pick a new origin. We'll change our color. Let's pick, it doesn't matter, you can pick this one or that one. Let's pick this one. Okay, in that case, you then say, where does it intersect my different values? It intersects x at 1, it intersects y at -1, and it never intersects z, it's infinity. So we say 1, 1 bar, and infinity, right? We then invert that, take the reciprocal of it, and that's 1, 1 bar, 0. And then we put round brackets on it without commas to represent a plane, okay? So what if we'd chosen this as a plane? Right? If we do that one, then this becomes the 1 in the x, sorry, -1 in the x. It's basically the exact opposite. It's -1 in the x, +1 in the y, right? So y, which one is it, right? So it turns out these are the same, right? These are the same plane. They're in the same family. It just has to do with where you choose your origin on these things, okay? If you choose your different origin in a different place and you draw it, you get the exact same plane in this case, okay? It's not always the case. That is the case here. All right? That is drawing and labeling planes. There are examples of this. So I'll post the link real quick, where you can see lots more worked examples if you so choose. Right here. Okay, continuing down our list. The next one was, okay, calculate atomic packing factor for a new crystal structure that you've never seen before. An image will be provided if you were given the ionic radii and the lattice parameters. So this sounds scarier than it really is. Let's go ahead and do it. We want the atomic packing factor. Okay. Okay, let's just work it with an example of rutile, right? what would be the atomic packing factor of rutile? I'm going to give you one that's a different crystal structure, but I'll make it clear where the atoms are located. For example, in class, we talked about where the atoms in rutile are located. We said that they are the following. They're the red ones, and that these ones, those are all on faces, meaning they're centered on faces, whereas these two are internal. They're totally inside the unit cell. And then obviously this one is also internal, and these ones are on corners, which are easiest to see. So if I was asking you to calculate the atomic packing factor of this structure, rutile, you would do the following. The steps you need to follow is you figure out how many atoms there are of each type, because they have different sizes, right? So you would say, okay, let's do titanium first. Titanium are these ones. There are 8 times 1/8 on the corners, right? So there are 8 times 1/8, plus there's 1 in the very center. Therefore, there are 2 titanium atoms or ions per unit cell. Oxygen, we know that the ratio is TiO2, so there should be 4 oxygens, but we can count them up to make sure. There's, just to change color real quick, there's 1, 2, 3, 4 that are half in and half out. So that's 4 times 1/2, plus 1, 2 that are completely in. Okay, so sure enough, there are 4 oxygens. On this problem, I would give you A, and I would give you B. Sorry, that's A, and this is B. So you know A and B, so you can figure out the volume of this unit cell. It's just going to be A times B. So the volume unit cell equals A squared B. And then all you need to do is figure out the volume of the different atoms, right? The volume of our atoms, well, that's going to be equal to 4/3 pi r cubed. That's the volume of a sphere. And you're going to use different things. You're going to use the radius of titanium, and there's 2 of these, plus you're going to have 4/3 pi r oxygen cubed, and there's going to be 4 of those. So that will give you your total volume of atoms, and the atomic packing fraction is simply the volume of atoms divided by the volume of the unit cell. Right? That equals the atomic packing factor, APF. Okay? That's how you do the atomic packing factor. So in the question, I will give you what the radii are for these ionic radii. I'll give you the lattice parameters, but it won't be a structure that you've seen before in class. But I'll make it clear that the atoms located in different spots, whether they're on faces, whether they're inside, whether they're on corners, whether they're on edge centers. I'll make that clear in the question. Okay? All right. Let's go to our next one. Our next question is the following. So it says, identify where ions touch in the crystal structures we learned about in class, and use this to calculate lattice parameter and sketch planes. So this kind of has to do with the question that one of the students said, saying they want to know everything about all the crystal structures, number of atoms, where they touch, things like that. So let's summarize. We've already talked about this in class, but let's go over it one more time. Where do the ions touch in crystal structures, and could you calculate lattice parameter from them? So let's just go through all the crystal structures that I expect you to know, that you might even potentially have to sketch in class, right? Start with FCC. Okay, FCC crystal structure. We'll do BCC. Okay. For FCC, the atoms are located at the corners, but they're also located on the centered faces, front, back, top, bottom, left, right. Okay. BCC, they're located corners and one in the dead center of the unit cell. Therefore, if we were to figure out where these things touch, in the FCC, when you were to shrink these atoms together until they touch, they would be touching along the face center. Whereas in BCC, they're going to be touching along the body center, right? the distance of these lines is not the same, right? In one case, you've got A, and this distance would become root 2A. In the other case, you've got A, you've got root 2A, and this becomes root 3A, right? In both cases, you have 4 radii equaling that distance, but that distance is different. Root 2A over here, and here you've got 4 radii equals root 3A. So that's how you figure out the ratio of ionic radii to lattice parameter for these two different crystal structures. What's the coordination number of the ions in these two different crystal structures? Well, in BCC over here, it's clearly surrounded by 1, 2, 3, 4 above and 1, 2, 3, 4 below. It has a coordination number of 4 plus 4 is 8, right? So the coordination number is 8 over here. This one's a little bit harder to see. You have to draw multiple unit cells, but it's actually surrounded by 12. The coordination number is 12. Again, the easiest way to see that is to draw multiple unit cells and then pick one, say like this atom up here. Okay. It is surrounded by, its nearest neighbors are that one, and that one. So there's 3 of those. And we know that it is connected to 8 unit cells. So at first glance, you might say, oh, 3 times 8, that's supposed to be 24. But that would be double counting because these are half in and half out of 2 unit cells. So it's 24 divided by 2. That's where the coordination number 12 comes from. Okay. The atomic packing factor, the number of atoms per unit cell. In this case, there's 8 times 1/8 on the corners. And then you've got 6 times 1/2. So there are 4 atoms per cell. Over here, you've got 8 times 1/8 plus 1 in the center. There are 2 atoms per cell. Okay, so that is that. What about some of the other structures we learned about? What about rock salt? Okay, rock salt looks a whole lot like FCC, except it's 2 FCC lattices that are interpenetrating and they're shifted. They're shifted by a little bit. So if we draw our first one, corners and faces, front, back, top, bottom, left, right. Now we're going to draw a second set of atoms. We're going to draw a second FCC lattice, but shifted, right? So those would be, if this was the new origin, we'd draw one right above it, there. This would, the face before now got moved over to the edge center, right? So these end up sitting right in all of your edge centers. Okay. So that is, oh, we're missing one. You would also put one in the dead center. Yeah, there's one in the dead center as well. Okay. So that's the rock salt structure. How would we figure out the lattice parameter ratio for the rock salt structure? Well, the lattice parameter, if this whole thing is A, well, A is going to be equal to, they're going to touch right along that edge. So it's going to be the radius of atom A plus the radius of your anion, oxygen, right? If that's what it is, times 2. So it's the radius of your 2 anions multiplied by 2. Okay. How many atoms are there per unit cell? Just like FCC before, there's going to be 4 atoms per unit cell, but now there's 4 of each, right? So there's going to be 4A and 4O ions. Okay. What else can we say about this? Okay, I think that's that one. What about cesium chloride? Cesium chloride looks just like body-centered cubic, except this middle atom is now a different type than the corner atoms, right? Therefore, in cesium chloride structure, you're going to have a similar ratio to this, but it's going to be slightly changed. Now it's going to be 2 radius A plus 2 radius, let's call it O. That's going to be equal to root 3 times your lattice parameter, right? Because now you've got 2 different sized ions. They're still going to touch along this body diagonal, but they're 2 different sizes. This might be your atom O, this might be your atom A. 2 radius of O, A, 2 radius of O, that equals the distance along there, okay? Let's see what else we needed to cover from this. Okay, there's HCP, that's hexagonal close packed. Hexagonal close packed's a little harder to draw, You start out by drawing the hexagonal plane on the top and the bottom, and then the next plane up, you place atoms directly above the, see these 3 atoms? Directly above that would give you the atom above it. These 3 atoms directly above it would give you that one. These 3 atoms directly above it would give you that one. You don't do it for all 6 of those because they wouldn't fit, okay? Therefore, you could say, what's the number of, well, what's the coordination number? It's 12, just like at HCP. We talked about that in class. You take this guy in the middle. It's got the 6 around him. It's got 3 below and 3 above. That's 6 plus 3 plus 3. That's 12 for coordination number. What about, let's see, what else can I ask about that? How many atoms are there per unit cell? You could say, well, there's clearly, well, first off, this is not the unit cell because there's a small, remember, unit cell is the smallest geometric shape that could be tiled to fill all space, and this is not the smallest. The smallest one is the subset of that that looks like this. Let me redraw that. That's the unit cell technically. 1 atom in the dead center of it, and atoms at the corners. So the 8 on average are 1/8 of the way in, then the 1 in the center, 2 atoms per unit cell. Okay, that's HCP. Where are the atoms touching? The atoms are touching along there, right? Because if we look down on the unit cell, it's this. It's just a, let me draw that a little clearer. This is the hexagonal close packed lattice, right? That right there is our unit cell, this smaller one. So it becomes clear that this distance A, that's just 2 of our metal radii, okay? A equals 2R in this case. 2R, okay? That's hexagonal close packed. Other ones we talked about that you need to know. You've got cesium chloride, sodium chloride. What about, oh, zinc blend, I think we just passed it. Okay, zinc blend is right here. I'm going to grab the structure and just paste it so it's a little bit easier. On this one, it looks just like FCC in terms of the yellow atoms, but we've started a second FCC lattice, shifted 1/4 over, 1/4 over, 1/4 over. So in the, it's shifted by, a second lattice shifted by a quarter, 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 okay? The coordination number of this one changes. It's no longer coordination number 12 or 6 like in cesium chloride or sodium chloride. Sodium chloride, if you take any one of these, say this this black one in the center, if you were to count neighbors there, it's now front, back, top, bottom, and left, right. It's actually 6 is its coordination number. But when we arrange it differently in the zinc blend structure, it's now coordination number 4, and it's easy to see that. For this center atom, you've got 1, 2, 3, 4 nearest neighbors. For all the atoms, it's going to be 4 in that structure. Okay, where are they touching? They're touching along the body diagonal. So if that whole distance is √3a, then over 1/4 of it, because this is shifted quarter, 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 so it's 1/4 along that distance, that's going to be equal to the 2 radii. Okay, so that's how you're going to relate those two. How many atoms are there per unit cell? Since it's FCC yellow, that's 4 atoms per unit cell, but there's also the silver, so there's going to be 4 silver and 4 yellow per unit cell. What else can we say about this? It's an open structure, right? Because these silver atoms are not occupying all of the what are called tetrahedral interstitials, which are just empty spots in the lattice. It's a more open structure. If these atoms are all the same type rather than being yellow and silver, this would be the diamond cubic lattice, diamond. What else can we say about it? Coordination number, radii, it's a lattice parameter, we got that all covered. Let's keep going. That's rutile. We've already talked about rutile in the last problem, so keep going. Perovskite. Perovskite is the last one I think that you need to know, and perovskite is super important because it allows a very diverse type of compounds to form in it. And the reason why is because you have a big site, you have a tiny site, and you have oxygen. So you've got room for big and small cations as well as oxygen, okay? So where would they be touching? It depends if it's a perfect perovskite or not. We talked about that it can be non-perfect. If it's perfect, then this distance right here, that would clearly be A over 2, right? It's going from the bottom of the unit cell halfway up. That's going to be equal to the radius of the B cation plus the radius of oxygen. Meanwhile, along this face, if those are touching, that would be root 2 times A divided by 2. That would be the radius of the A cation plus the radius of oxygen. Okay. How many atoms are there per unit cell? There's one B in the center, right? There are 8 times 1/8 A's, so that's 1 as well. And then there are 6 times 1/2 oxygens, so that's 3. So it's a 1 to 1 to 3 ratio. We sometimes call this the AbO3 or X3 type structure. Okay, that's perovskite. What else? Coordination numbers. The coordination number of the B cation in the very center, that's easy to see. It's surrounded by 6 oxygens. What about the oxygens though? What's their coordination number? Oxygen, if you look at it, they are closest to titanium. They're not closer to A, they're closer to B. And so the next unit cell over there would be another titanium, but their coordination number is 2. Okay. The coordination number of A is going to be 12, right? It's located on this corner. So again, it's got the 1, 2, 3 that are closest to it. It's closest to, it's at the intersection of 8 unit cells, 8 times 324, but each of those are half in and half out. It's coordination number of 12, just like FCC. Okay, that is that. Let's go to our next one. Calculate planar density for a given plane in one of the crystal structures we covered in class. Okay, so let's do that. So let's just take perovskite since it's here. Let's take this plane. I don't actually remember what I put on the test, so I hope this isn't the same. But let's do it anyways. Okay, that plane, the one that all those oxygen and the B are lying on. First off, what would be the name of that plane? Pick an origin. Pick that back corner. It never intersects X or Y, and it intersects Z at 1/2. When you invert that, that would become the 002 plane. Okay, the 002 plane. So for like the 002 in perovskite, we could sketch it. Looking at that, it's going to be atoms. Remember, oxygen is big. The silver atoms here, these are big. You got your B right in the very center, and then your other ones. So if this is A, and that's A, it's going to look something like this. I'm not the greatest artist ever, but it would look something like that, where this is your oxygen, and that is your titanium, or whatever your B atom is. Okay? So that's the sketch of it. What about the planar density? Planar density, you're going to take the number of atoms, not the area of the atoms, the number of atoms. In this case, there are 2 atoms, right? One B atom and 1 oxygen atom. So it would be 2 over A squared. That would be our planar density. Okay? All right, let's do another one. Okay, use diffraction rules such as all even or all odd, or that they must add up to even, or whatever the case may be, in order to calculate the first 4 reflections of a crystal structure. I think we can do this because we did an example of it in class, and we'll do another one right here. But here's how you go about it. Give ourselves some room. Okay. All right, when you do this, the rule of thumb is to remember that if you're looking at your diffraction pattern, which is intensity as a function of 2 theta, that the peaks that you see, right, you're going to see different peaks. These ones down here correspond to a large interplanar spacing. Okay, so you've got your large interplanar spacing and your large and your small interplanar spacing. We know that because lambda equals 2d sine of theta, right? So if this over here is a constant and you want this to be small, then you want this to be large, okay? Therefore, take your crystal system, let's say it's cubic, right? If you've got a nice cubic system, then 1 over d squared equals h squared plus k squared plus L squared all over A squared. If it was not a cubic system, then the formula gets changed slightly, okay? In any case, if you want D to be as large as possible, you can choose H squared plus K squared plus L squared to be as small as possible. Now that for cubic only, okay? If this was a different crystal system, right? Where is our table? If we come down here to our table for non-cubic systems, then what you want is for this entire term on the right-hand side, okay, right here. Cubic, it's easy, right? You want this to be as large as possible for this to be small, or for this to be large, sorry. You want this right-hand side to be as small as possible for this to be as large as possible. If we were, say, in an orthorhombic system, you'd want this whole right-hand side to be as small as possible to get the largest possible DHKL, okay? So over here, what we're gonna do is we're gonna write out all the HKLs that are allowed. Well, just, yeah, HKL. Write out ones that are allowed. Let's write out h squared plus k squared plus L squared, okay? So what's the rule we want to follow? Which one did we do in class? Let's do the other one that we didn't do in class. So in class, we did an example of, right here, we said for FCC, so they had to be all even or all odd. Let's do ones where they have to add up to an even number then. Let's do the other one. If they have to add up to an even number, well, so we're going to say must add up to even number. All right, well, let's start picking things. Clearly, something like 100 doesn't work because that doesn't add up to an even number, so we don't have to include it, we don't have to consider it. But 110 does work. So does 200. So does 211. So does 202. So does 222. What else? We could keep going. We could say 400. We could say 411. 420. That's a bunch. I think that's gonna be our lowest ones. Let's start adding up h squared plus k squared plus L squared. In that place, it's gonna be 2. That's 4. This is gonna be 6. That's gonna be 8. It's gonna be 12. 16. That will be 18. This will be 20. So we happen to write these in just the right order, actually. 2, 4, 6, like that's an increasing order. So the smaller the h squared plus k squared plus L squared, the larger the d squared, right? So in this case, the question was asking, you know, figure out the first 4 reflections. Assuming we haven't missed any, which I don't think we have, that's our first 4 reflections, because those are the 4 smallest h squared plus k squared plus L squared values. Now, if this was not cubic, if it was tetragonal or something, then we'd have to slightly modify this, because now you can't just go off of this alone. Because in cubic, let's go over to it, in cubic, those were all divided by the same number. So it didn't matter what A was, because they were all divided by A. But take orthorhombic, if you want DHKL to be as large as possible, then you want this whole right-hand side to be as small as possible. So you can't just look at h squared plus k squared plus L squared. You have to include the lattice parameters in your calculation, okay? Same thing with tetragonal, same thing with all of them, okay? Except for cubic. So that would be how you figure out the first 4 reflections for a crystal structure, okay? All right, let's do the next one. Use Bragg's law to determine the 2 theta position of an XRD reflection, okay? This will be the last one we cover without any follow-up video. Okay, so for this one, and how are we on time? Yeah, we're doing okay on time. Okay, use Bragg's law to determine the 2 theta position, right? So let's say that you figured out these 4, but now I want you to actually report the 2 theta value of those. And you say, okay, great. Let's assume this is a cubic crystal system and the lattice parameter is equal to 3.6 angstroms, right? Fair enough. So 3.6 angstroms. Then to figure out our diffraction, you'd say that the Bragg's law says that the wavelength is equal to 2 times the interplanar spacing multiplied by sine of theta, or in other words, sine of theta in degrees will equal lambda divided by 2d. Lambda, if it's copper radiation, then it's 1.5406 angstroms divided by 2d. So we would just figure out d, right? From above, we know that d squared for these things, d squared is just equal to a squared divided by all of that. Therefore, d is just the square root of that. So it's going to be the square root of a squared divided by that number. Okay? So we could punch those things in. I'll just squared divided by 2. All right, that's our d value for that first one, which is 2.545, right? So in this first one, it's going to be 1.5406, 2 times 2.545, which equals that's equal to 0.605. Okay, that comes out to 37.24 degrees. Multiply that by 2, and that gets you your 2 theta value. Okay, so that's how this approach works. So 2 theta is equal to 2 times 37.4 degrees for this first one. And you would do that for all these if that was what the question asked. Okay? All right, that's the review. If none of this was clear, or if you want more information, first off, there are a bunch of YouTube videos on this stuff that I will post in here. But if I can explain anything else in further detail, I'm happy to, or I can do a follow-up video making something else clear. Okay, I will see you in class tomorrow.